Okay, so let's begin with a quick forward to the talk. The topic itself is quite narrow and focuses almost solely on one of the new features in TypeScript 4.1, which are template literal types. And beginners might have some difficulties in following the implementation step by step. But in the same time, I'm happy to take questions from you. And for everyone, I hope this is going to be also a motivation to explore some advanced types on their own and learn something new after this talk. My name is Michał Załęcki. I work remotely as a senior engineer at Hotjar. I focus on unit testing, software design, and architecture. I write, and you can read about those topics on my blog. The link is on the slide. And in case your interests are familiar, you can also follow me on Twitter. I also used to organize a local React.js Wrocław meetup during like sweet pre-COVID times. So let's go to the agenda. So what are we going to talk about? First of all, we will start with what is a literal type. What can be like a basic use case for template literals feature, for the new feature. What like we will stop for a little bit to like discuss like what the inference and how the type inference works for template literals. Also, I've prepared a little bit more advanced example walkthrough of the implementation of one type. And if we have enough time, we can take a quick look at how the community took this new feature to the extreme and implemented some crazy stuff with it. But let's start from the beginning. By definition, literal in programming represents a fixed value in your source code. So that would be like a number, string, or a Boolean value. So on the left, we have examples of primitive types that we don't have to specify the type explicitly, and TypeScript compiler infers the type itself. So you should see my cursor. Can you see my cursor?
Yes.
Okay, cool. Thank you. Thank you, Jakub. So here okay. Here's the first variable. Nothing crazy here. At TypeScript meetup, you should probably all understand that, but this is going to be for like showing you the difference. So here, like if we assign a string to a first name, TypeScript kind of knows that it can infer string for this first name variable. Similar for the numbers and Boolean values. So you can like assign different number, you can assign different strings and different like you can assign either false or true. But for template literals, it's a little bit different story. So on the right, we have examples of literal types. We declare literal types by marking down them either as const or explicitly, like on the line 6. So here, like if we create a string but put as const after the value, the TypeScript is going to infer that the type of the first name variable now is Bob string, not like just any kind of string. So trying to assign a different string is going to result in a type error. We can also explicitly give the age variable the type 18. So now the 18 is the only number that this variable can accept. And the same story for Booleans. And type literals in and of itself are not very practical, but their properties come in handy in combination with unions. So pay attention to the dispatch function declaration, and here we can see that like if that string would be inferred to just string, the union type of string or string wouldn't be very helpful, but using literals, you can easily limit the type of the action attribute that this given function can accept. So like create, update, or delete are like valid strings that this function accepts as section parameter, but the read is not, and thus we get type error. Now moving to a basic example, imagine that our task is to create a type of the function that accepts CSS class name that comes from Animate CSS library. For those who don't know, this is just like a library of CSS classes that can, like, if you assign it to the HTML element, this is like going to do some like fancy animation. So we quickly realize that this task requires a lot of manual labor, and defining each class separately is not going to be fun. In the library, there are a lot of more classes than in this example, as this only covers the fade in and out animations. So you typically have to define by hand or by some like copy pasting all classes that the given kind of animation accepts, and then just like create the union type by hand, and then like pass it to the element, pass it as a type of the element, sorry, the class name argument. Typical, at least according to me, use case for template literals as like a feature is going to be concatenating different string literals to create more extensive union types. So instead of specifying each class separately, we can leverage repeating substrings, which this feature basically is. So let's try to understand how it works. False fake class names is a union created using template literals. So let's try to like analyze how it gets built and how it gets to those like string as how this union type is built, and how this mixed bag of like strings ends up being those like actual classes. So the process is quite simple. We look at this type. So it starts, the string literal starts with a fade. So here's our fade portion. Next, we're going to see what are the possible values for the entry type. So it's either in or out. So we take the first one, it's in. We don't end here. We like keep looking what's next. But here we see there's an empty string. So that's the empty string is the first element of this entire union, and there's nothing after. So at that point, we just like end inferring this string, and that's our first like case. How do we get to the second case? So the process is similar up to the point where we check for the empty string, but we already used this variation, and we go to the next one. So we look at the direction, and the first string in the direction type literal is down. So we take this one and we are going to see what's the next, and the next is like empty string or big. So we take the empty string and we end here, and the entire process like repeats for the next occurrence. So instead of like empty string here, we will take a big and create another case. So that was a lengthy explanation, but I hope it clicked for you by now. And to understand advanced example, before we do that, I would like to make sure that we have some intuition about how the type inference works in conjunction with conditional types. And here enters the infer keyword. So we want a type that accepts any promise and returns a type to which the promise resolves. So here we have like this unpack promise, and we going to limit the T type and make sure it's like any promise that resolves to like anything. What we do next, here enters the conditional type. So we check whether our type T extends a promise. We like kind of know that because we limit it only to promises, but that's the syntax. And in place of where the n was, we just like put this infer r. R is an arbitrary type name. It doesn't have to be R, but by convention, in many examples, you will see R used as a variable for a type. So if the type T extends promise, then in R, we are going to store the type to which the promise resolves. And this is not really something special towards like promises. You can like do this with arrays too. And if that's true, and it always is, we just going to return R. If that wouldn't be the case, that's the way how the conditional types are implemented. It makes us to return never. In the correct program, we are never going to have a variable of the type never. So you don't have to like worry what to do with this case. If the type is implemented correctly, you will never get this as an output. And now you can just see that like calling unpack promise with a type promise number is going to give us a number. So that's the basics of like how type inference with conditional type works. And we can use the same technique to infer template literal types. So here we create this in or out type, which accepts any type of T. We could like limit that to like string or something like that, but it's not that important for this example. Now what we want to do is we want to make sure that T extends some string that starts with fade, and then we want to store the rest of the string type, literal, in R, and just return R or never. So that's why the result of calling in or out of like fade in is going to give us in, and in or out is going to give us out. So we effectively just stripped the prefix fade using that type. So here's a similar example, but now additionally with fashion, which gives us much more flexibility in text transformation. So here we're going to implement the type, which is like works as a typical function. We're going to accept some string, n string, and we're going to infer like if this string is some string with empty space, like space is always empty with a space, then we just like going save everything in R without the last space, and then we're going to call trim right again. So this way we're going to like continue doing that until we have a string that doesn't have an empty space at the end. So we just like return T type. The result is like if we call trim right on the string, we're going to get the same string but without spaces at the end. So I think that's pretty cool. And for advanced example, we up our game and going to implement a fixture function with the following very simple API, which is going to return objects of type that corresponds with the keyword in the past phrase. So this, like, please try to remember this interface. It's not going to change for a while. It has like user, which corresponds to the type user, and key order that corresponds to the order type. It doesn't really matter what those like domain objects really are. It's just like some interface. And here we see our first goal for the implementation. When I call it with user list, I want to have an array of users, and when I call it a single order, I want to get one order object. If you are not familiar with the idea of a fixture, this is like a fixture. It's like an object that you can just play with in tests. This is like a factory for some dummy objects used in tests, for example, or any sort of test. So the naive approach would be to define a type for each possible input. So for example, by overloading the function type, we could do that without fancy template literals. So here I declare the function for each phrase that I'm expecting this function to accept, and thus I get the same result, but it is quite naive approach, but it works, right? So let's try understand functionally the same type, but now that's using templated literals. So I declare a function which, and I will need two types. The type K, which is key of entities, so it's going to be either user or order, and the type T, which is going to be that phrase that user is providing. Going to infer that you don't expect this type really to be called with any arguments. We will just need them for type inference later. So, and I can now declare what this type actually returns. So first step in achieving this our small goal is making sure that we want to make sure that what the user provided us is either single something, which we're going to store under R, or it's something list. So once we decide on one of those, let's assume that it has been called with single user. So I know by this point that user is stored under R, but we know that because we understand the implementation, but TypeScript requires additional check, which makes this code less readable. I hope they will get to the point at which this isn't needed, but right now we have to make sure that R extends K, because there is no direct link between what we infer here, so what this type is, and it doesn't really relate to this type. So that's why we need to, although we know for TypeScript, we need to make sure that R extends key, which is R if R equals K. Then we're going to return the type of the entities interface using this key, so either user or order. The else case is really similar. The only difference is that we know it's about the list, so I'm going to return an array of those entities from by the key. So this way we get to this implementation. And the benefits of using template literals might not be apparent just after the previous example, because there was a lot of more code to achieve the same. And even if it wasn't that much characters, that much more characters, it was much more difficult to understand. But here we start to see how additional flexibility that comes from template literals makes it easier to implement further changes. So the additional requirement is to allow the consumer to pass additional text, so we can influence the returned object by some predefined modifier. So I'm going to expect users to provide me with some modifier, keyword, and list, or another modifier, indication that this is a single object, and a keyword. So the only difference I really have to make between this one and this example is like, first of all, I'm going to change entries interface, because now it's not just like user order. Now it's some function that accepts a modifier. And what this implementation is going to do, like this is going to, like, I'm going to implement somewhere else. It's not part of this like typing exercise. But we can imagine that there is some function which accepts modifier, either like empty string, random, or invalid, and returns a user type. And the same for order. So it might be like email, maybe invalid, like for random, maybe some like ID is going to be randomly generated instead of hard-coded one, and so on and so on. For the simplicity of creating this type, you see that random has additional space and invalid has additional space, just because that's how like it's simpler for me to just like build those strings. But I also have the modifier, and I can nicely combine this with our trim right that we've implemented earlier. And now under modifier, I have just like empty string random without the space and invalid without the space, just because like we've trimmed it. So here's the type for those functions. And the only thing that we've changed with regards to the previous example, we're going to add match modifier here and going to add match modifier here. So we limit what user can actually pass to what we know how to handle. And here's the copy paste. I like still just like I can accept additional string here, and that's it. I'm doing the same here. The difference that I cannot just like call entities from R. I have like, because this is going to be now a function, but TypeScript provides us with this return type, which accepts a function type and just gives us a return type of the function. So this effectively is going to give us either user or order type. So that was our advanced example, but it really isn't that complex if you look at what the community came up with. So the query selector is like an example I like. It's like good to like learn something new, and here it is. So what maybe I will make the text a little bit larger. So what this guy implemented was the type for the query selector, like document query selector. So it just like strips everything and gets to the point at which he can infer that by passing such string, we're going to get an HTML anchor element if we call it with a comma. We're going to get either an input element or div element, and so on and so on. It works even with SVG elements. So pretty cool, but it's basically working on the very same assumptions that we had. There's some like splitting, there's some trimming, composition of types. So like if we have like trim left, trim right, we can like compose them into one and have just a trim, stripping by modifier. So like you can get rid of those like different commas, like brackets and stuff. So that's cool, but not that far off what we've done, just like more. There's also like a JSON parser. I think that was like my first like, oh, whoa. But what the guy did was he basically implemented a very simple parser. So you pass JSON as a string, and it gives you an type of the JSON. Pretty cool. But what's really impressive, and like using all sorts of different like tricks, is like SQL database that someone implemented using TypeScript type system. So this is rather long. I'm not going to take that much of your time and try to explain it, but let's see how it works. So here you define a concrete type and mark it as const. So it's not just an object with some like keys and of arrays of some like random types. Those are like concrete types of those objects. So that's our input to the database. And what happens now? That's our like database data basically. So we store it as a DB v1, and there's this query. There's this query type which accepts what is just like a simple SQL query, and it gets you. So here, select. We are going to select first name as name from people. So from this array, where last name is Simpson. So we have few Simpsons, and here they are. So you know them from like the Simpsons movie. Again, here, we already covered that. So now we want to have like objects of first name and last name. You can do that for like characters that have a child, stuff like that. It can update also, and after you make a query with an update, now we set like first name to Milhouse, where the ID was 8, so that would be here. So it's not Milhouse, it's Milhouse now. And where was it? Here. I can expand that, but then we query for that field. And here you can see that it's actually Milhouse now, not Milhouse. So that, I think that's pretty cool. Of course, this is like abusing the feature. No one really is going to do that. It's going to be slow and hard on your compiler, or rather on your machine. But nonetheless, I think it's like super creative. So there's like all kinds of different tricks and optimizations to like make it less suck in terms of performance. Some shortcuts like defining array of indentations, so you can just like strip quicker, for example, and not just like by one, because the recursion has some limits. I think it's like 32 calls. So if you have like really lots of spaces, you can trim faster, stuff like that. If you are interested, there are more examples on this GitHub repository of some template literal types. If you type it in Google, that's going to be the first result. I prepared, or either if you are like interested in revisiting the code examples, I encourage you to read the blog post where I explained the advanced example step by step, a little bit like in more details than I've covered right now. And also I explained the recursion there a little bit in more details. So if this is something that interests you, I encourage you to read the blog post. I've also shared it on Twitter, so you can find it there. And thank you. If you have any questions, I'm happy to take them.
Awesome. Thank